All right, happy Friday. Those of you that are here in the classroom, you made it almost a whole week of being in school. It's pretty cool. It's going okay. So your quiz yesterday, I have them graded. I just didn't place them in PowerSchool yet. If I have time at the end, I'll pass them back to you so that you can look at them. I'll have to collect them again. Those of you at home, I will open those up to you and release your grade so that you can also look at your quizzes. But hopefully I can at least pass them back so you can take a look at them, and then I will collect them from you so that I can place them in PowerSchool next period. But they were pretty good, and I think those of you that took it on paper, it seemed to be quicker on paper. I don't know if it's like the moving the screen, the zooming in and out, and I don't know if that takes longer to upload or what, but the paper seemed to be a good experience. I'm doing it again with 2 of my classes today, and then next week I'll be my honors Trinity Cal classes will be taking a regular old test on paper as well. So that'll be kind of moving forward what I will be doing, giving tests on paper. The rest of it still will be in the iPad. They don't want us using a lot of paper in the district, but I think some things definitely need to be on paper form. I was able to grade it a lot quicker on paper as well. So every quiz or test that I grade, like it uploads once and then it uploads again for me to edit, and then it has to save. Like it's a lot of extra uploading. Me just waiting for it to upload. So today we're going to start talking about the second half of the chapter, which deals with a new function, the inverse of the exponential function that we've been working with is called a logarithmic function. We need logs to solve for exponent functions. So that's why the logarithmic function was created. Remember, inverse functions, they kind of have like opposite operations. So multiplication versus division. X squared versus the square root of x. So they definitely have a relationship. Those functions are grouped together or related with each other. And we are going to be looking at this logarithm function and trying to see how it is related to the exponential function. And it really is there so that we can solve for exponential functions. So that's the whole goal. And I solve for that exponent when it's in the x location as an exponent instead of using the calculator. So we will talk about that. These functions, actually, we can convert from one form to the next. So it's kind of a little bit of conversion, going from one equation and switching it, transforming it into its inverse equation. And we'll talk about how to do that today. And then we'll look at evaluating logarithmic expressions without using a calculator. On Monday, we're going to continue this section and we'll talk about finding inverse equations and finding inverse functions, and we'll also talk about graphing them. So what does the graph of this function look like? So we'll do that on Monday. So homework tonight is in the book, and it actually is not a lot of work today. You'll see that the problems that we go over are one-step problems. So it's usually rewriting the equation, and then it's a little equation that you're going to be solving for x. So like one step. And then another reminder, the factoring review worksheet that was assigned yesterday after the quiz is due on Monday. By the end of next week, we will use factoring to be solving these logarithmic equations. So that factoring, as I said, once we did it in chapter 4, like we continue to use it in every chapter. We'll use it again in chapter 8 as a means to solve. So a lot of functions, a way to solve those functions is by using factoring. Even if the quadratic function or even if the equation doesn't start out as x squared, somewhere in it is embedded a factoring to solve. So if you can go in your packet to section 7.4. Section 7.4 does involve a lot of information, so we'll split it apart over a couple of days. And the goal here, it says, is to evaluate logarithms and to graph logarithmic functions. So the first thing that I want you to think about is what we've been doing, which is the exponential form. And an exponent is that number, the base raised to a power. So the base is called the 2. The power is also a 2 in this case, but that's an exponent. And Ava, we know that 2 squared is 4. Ava, 2 cubed is 8. How about 2 to the x equals 6? Do we know a power of 2 that would make the number 6? Could you guesstimate a power of 2 that would be close to the number 6? Cody, could you guesstimate that? What would it be between, probably? Yeah, we know it would be between 2 and 3. But we don't know a power of 2 that's going to make the value of 6. This is a true exponential function because the x is in the exponent location. And that's what we worked with in the last chapter. So the goal is for us to be able to figure out what power of 2 truly does make the value of 6. So is it 2 to the 2.3 or 2 to the 2.4 or 2 to the 2.5? We don't know. And we're not just going to literally like plug numbers into the calculator. So that is why this function called a logarithm function was created. So that we can determine what that x is without just saying, oh, I need to graph this in my calculator. So there is a way to find out that value. So that takes us to the little definition of a logarithm with a base b. So the number here, the 2, that is our base. When we were using an equation in exponential form, we always said y equals a b to the x. Well, the part that contains the exponent is really the part that we're focusing on. That's the base. And think, it's a b, so b represents base. A, the number in front, we always said that was just the initial amount. We're not really focusing on that because that doesn't have the exponent. So let b and y be positive numbers with b not equaling 1. So we're saying we now have y equals b to the x. B can't be 1. What happens if b is 1? Yeah, the answer would just be 1 because Riley, if you took 1 to the 99th power, you still get 1. And then it wouldn't be an exponential function because 1 to any power is just the number 1. So b can't be 1 because then it's not an exponent. So b cannot be 1. Our base can't be 1. The logarithm of y with base b, and then they give you the way that we will write it. So we have this log with a little base of y. It says is defined as the following. Log base b of y is equal to x. If and only if, so that's a conditional statement from geometry. If and only if means that both sides of the statement need to be true. So log base b of y equals x if and only if b to the x is equal to y. So essentially, this logarithmic function exists when our exponent function b to the x is equal to y. Now, I want to kind of make sure that you see how we're reading this. It says the expression log base b of y is read. Maybe highlight this because you're going to have to learn how to say this. So we say log, and then the little b is the base. It's a subscript, so it's lower than the actual log. So the base is b, and then it's always of y. So that's how we would say log base b of y. So we're going to try and look at the two forms and just start with converting them first. So can I take the exponential form and change it to logarithmic form? Or can we take the logarithmic form and change it to an exponent? So these two functions are inverses of each other. They're opposite operations, just like an x squared and a square root of x. So opposite functions, opposite operations. The first example here is trying to just get you to think about these forms. And we're going to do a little conversion. Those of you that have chemistry, you do some conversions in chemistry, converting units. So we're going to do some conversions in math as well. So the first thing that I want us to kind of think about is the exponential form of a function. And that exponential form is b to the x equals y. So that's the exponential form. The logarithmic form, this new function, is log base b of y equals x. Last chapter, chapter 6, we talked about finding inverse functions. In order to find an inverse, you switch x and y. That was the first step to find an inverse. You took the x, you took the y, you flipped them in the equation. So if you notice in my equation, b to the x equals y, my y and x are now flipped. So this exponential form is equal to y. The logarithmic form is equal to x. So you're switching x and y for the inverse function. I'm going to show you a couple of different ways to also think about it as we work through the examples below. But it wants us to convert from logarithmic to exponential, or from exponential to logarithmic form. And if you look on the left, part A, it gives us a log. And we're going to try and write it as an exponent. So we have this logarithm form, log base b of y equals x. Our problem says log base 2 of 32 is equal to 5. We're going to write this as an exponent. And right up here is my exponential form. One way to remember how to write this is to actually make an e within our logarithmic form. And we're going to start with the base to make my e. So I want to write this as an exponent. When I write it as an exponent, I'm starting with the base of 2. My exponent is a 5. It has to equal 32. So I'm kind of making an e as I'm thinking about how to write this in exponential form. So I'm going to go over that again. To write it as an exponent, the base of my exponent has to be a 2. The exponent is actually 5. I'm crossing over the equal sign and then through the number 32. And now I have exponential form. When you write it as an exponent, it should make sense. It should be an expression that is true or an equation that is true. Brooke, does 2 to the 5th equal 32? Yes. So the exponent form of a log is 2 to the 5th equals 32. As a log, that means log base 2 of 32 equals 5. You can see that the base is the same. So the base is 2. Those are both called the bases. The base of an exponent, the base of the log. And then these two numbers switch because those are my x and y's. And to write it in exponential form, they need to switch. Questions? So if you look at the next one, we just go back and forth here to get you used to writing this. We have exponential form, 1,000 equals 10 cubed. That's true. 10 cubed is equal to 1,000. I'm just going to flip it and say 10 cubed equals 1,000. One more zero there. We want to write it as a log. So now we want to write it in log form. Ella, how could you take that exponent and write it in log form? Excellent. So let's look here. The base is 10. Whatever's connected to the exponent is the base. So right here is our base of 10. These two need to switch locations. Y and X need to switch. So log base 10 of 1,000 is equal to 3. Questions? So the third one is back in log form. Log base 7 of 1 is equal to 0. So if it helps you to draw the little e symbol, so I'm writing it in an exponent. My base is 7. My exponent is 0. Crossing over the equal sign, and then it equals 1. So Gabby Soul, 7 to the 0, does that equal 1? Yeah, of course it does. 7 to the 0 is equal to 1. So again, the base is in the same location. Oops. I have a 7 as a base. We have a 7 as a base. The X and the Y has switched. Part D says 1/2 equals 2 to the negative 1. And if it's easier for you to think about it as the exponent on the left, 2 to the negative 1 is equal to 1/2. So Jordan, how would we write that as a log function? What number is connected to the exponent? 2. So that's the base. So the 2 is the base. And then, there you go. Flip flop the numbers. 1/2 equals negative 1. So again, the base is the number with the exponent. So that's the base of our log. And then we have to switch the numbers. So you're switching X and Y, those numbers flip flop. The last one here, part E, says the log base 13 of 13 equals 1. Helene, can you write that as an exponent? Okay, 13 to the first equals 13. So my base is 13. Exponent is 1, my equal sign, and then 13. We will use these conversions a lot. We will convert from one form to the other to help us solve equations. And if you look at the 4 examples underneath, these 4 problems want us to evaluate. Evaluate means simplify, break down to the smallest form. And we're going to use the exponential form to help us. So if you look, we have the log base 3 of 81. The first thing I want you to do is just set this equal to x so that I have it equal to my x value. That's what we're going to solve for. So log base 3 of 81 equals x. In order to find x or evaluate this, we're going to actually write it as an exponent because we can think in exponential form. We spent 2 chapters working with exponents, chapters 5 and chapter 6. Brooke, how can we take log base 3 of 81 equals x and write it as an exponent? Yeah. So she said 81 equals 3 to the x, or we could say 3 to the x equals 81. Either way, it's the same exact thing. It just depends on where you like seeing your exponent. So the base is 3. The exponent is x, and it's equal to 81. So if you still have that common power sheet, you can use it. You might already have this memorized. We want the power of 3 that equals 81. Brooke, do you know what power of 3 is going to equal 81? 4. 3 to the 4th is equal to 81. 3 times 3 is 9. 3 times 3 is another 9. 9 times 9 makes 81. So evaluating means break it down. My x is going to be equal to 4. My logarithm is equal to 4. Looking at part B, we're going to do exactly the same thing. Set it equal to x. Jaden, can you write this one as an exponent?
So would it be 4 to the x equals 0.25?
Yeah. Now let's talk about that 0.25. How could we write that as a fraction? 1/4. So let's keep it, instead of as 0.25, let's say this is really 4 to the x equals 1/4. Now think about exponents. What power of x would take a number that's a whole number and make it into a fraction? You know, Jaden?
A negative
A
exponent.
negative exponent. Negative exponents make numbers fractions. So Jaden, 4 to the what power makes it equal to 1/4?
Negative 1.
-1. So anytime you have a fraction, there's a negative exponent involved. 4 to the -1 is 1/4. A negative exponent makes a number under 1. Why don't you try C and D? So notice there's a 1/4 in C. So we'll have to think about that negative exponent. So try and rewrite it. And then also try D. If you want to do D first before C, you can try that as well. These two will make you think a little bit. Julia, could you write it part C as an exponent? Right, 256. All right, so we have a fraction. We want to make it into a whole number. So is your exponent going to be positive or negative? What do you think, Abby? It's going to be negative. So the x has to be negative because it is a fraction and I want to take it out of fraction form. So it's going to have to be a negative x value. So I could really say 4 to the negative x is equal to 256. That's another way I could think about it. So my x is going to have to be negative in order for my value here to be 4 to some power equals 256. Anybody know what power of 4 gives us 256, Gabby? 4. So x is going to have to be -4 because when I plug it into my negative x, I would have 4 to the -4 equals 256. So my exponent has to be negative because it was a fraction form. To get it out of a fraction, I need a negative exponent. The last one on here, part D, says log base 47 equals 7. So Lacey, how could we write that as an exponent? All right, so we have to think, what exponent of 49 would make 7? Lacey, do you know? You're going to phone a friend. Yeah, it's going to have to be a decimal. Can you phone Faith? Phone a friend? Why 1/2, Faith? Yeah, that one thing we learned back in chapter 6, when you have a fractional exponent, the denominator becomes your radical. So 49 to the 1/2 is really the square root of 49, which makes 7. Look at that, crappy math. You learn it and then you still have to use it. So last chapter, we talked about fractional exponents really being radicals. So a 49 to the 1/2 is the square root of 49. So my x must have to be a half. questions on any of those, Jaden? No, you're good.
For like the final form, like what your answer is, would it be like the x equals part, or would you have to like rewrite it in the original?
No, you can just keep it because you're simplifying, breaking it down. So you can keep it as x equals 1/2.
Okay, thank you.
If you wanted to come back up here and say equals 1/2, you could totally do that, but not necessary. Other questions? All right, so on the next page, there are two versions or forms of logarithms that your calculator contains. The one is called the common log and the other one is called the natural log. The common log is a logarithm with a base of 10. So a common log has a base of 10. So that means I would have log base 10 of y equals x. In your calculator, it's the one that says LOG. So if you look on your calculator on the left-hand side, you see LOG. That is the log with a base of 10. So anytime you have a function, if you look down here, look at letter A, it says log 8. If there is not a base given to you, it's implied to be 10. That's the common log. So even though there's not a little base sitting here, it's implied that this is really log base 10 of 8. So in your calculator, if you type in the log, hit the log button, and then type in the number 8 and hit enter, it'll give you the value of the log of 8. And Jaden, what number does it give you when you type in log of 8?
49.
So again, on your calculator, it is on the left side next to the number 7. And literally, you're just hitting that number. So you get 0.90308, blah, 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 blah. So anytime you see a log missing a base, that's the common log. It's implied to have a base of 10. The second type of log is called the natural log. In section 7.3, we discussed the natural base. So the natural log is the log with the natural base. And that natural base is the value e. E is called the natural base. We calculated that number e by using the interest formula. And that Leonard Euler man, the mathematician that was born in the 1700s, is the guy who created the natural base. The natural log gets written a special way. So the common log is just log. The natural log, you can see in part B, is an ln. Now, why is it not NL? I have no clue. I'm figuring that we're talking about a log, so they wanted to keep it L to have the log first, but ln is the natural log. So the log natural is really how we're thinking about that. The base is an E anytime you see a natural log. But again, that base isn't going to be written, it's going to be implied. So if you look at part B in example 3, we have the natural log of 0.3. So in your calculator, you'll see the natural log, ln, and e are connected together. We were using the e button last chapter or last section. Now we're going to use that natural log, and they're in the same function because they're inverses of each other. So if you type in the ln, and then I think it was 0.3, You get negative 1.2039, blah, 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 blah. So negative 1.2. So both of these logarithms are special logarithms. So if it's the log by itself, it's implied to be a 10. You can use your calculator. If it's the natural log, the base is the e, and again, you can use the calculator. All of the other ones, you can't use the calculator for because we can find those actual values. They can actually be created using an exponent form. Correct. Yes, sure. Most definitely. You can place the base in, especially once we start like evaluating and moving back and forth. So we're going to do one more example. I'm actually going to skip the inverse function. We're going to come back to this on Monday. So I'm going to skip over this for a minute. I want you to look at example 5. I should have these flip-flopped in the notes. Example 5 says solve the equation without a calculator. If the base isn't given, and it's listed as an x, how do you think you would solve this without a calculator? What do you think you could do with the log base x of 81 equals 2? So how can I try and solve that? Gabby Sola, have an idea? Yes, when in doubt, write it with what you know. We know exponents. We've worked with them a lot. So let's put it in exponential form. What would that look like, Gabby? So what is x equal to? 9. So if you don't know what to do with it and it looks kind of crazy and you're trying to find that x, write it as an exponent. 9 times 9 is 81. So my base would have to be 9. Log base 9 of 81 equals 2 because 9 squared is 81. Looking at the second one, we have log base 3 of x equals 3. Grace, how could we write number 2? No, you said you're good. Good. So what is 3 cubed? 27. Riley, how about number 3?
Would that be 2 to the x power is 8?
Yeah, 2 to what power makes 8?
And then it'd be 3.
Perfect. And then our last one, Ella, what do we have here? Log base x is 64 equals 3. X equals 4. Any questions? So I am going to stop there because I don't want to start inverses without really giving it a true amount of time. So we'll talk about the inverse function and we'll find the inverse function. And then we're going to talk about graphing on Monday. But your homework, like I want to let you know that this homework should be pretty straightforward. So example 2 is the first group of problems from your homework. You're going to be converting it and evaluating. Don't rely on that calculator. I said the second half, like the test that you take for chapter 7, will be a no calculator test. So try and not rely on that calculator. Use the common power sheet if you need to use that. The other group of problems are going to be like the little equations where you're not using a calculator. And then there's a small group just to get you used to like plugging in numbers into the calculator as well. So I'm going to pass back your quizzes. Those of you at home, anybody have questions? All right, so if you're at home, have a fantastic day. You can go to Google Classroom and check any comments that were made on your